Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. Today's episode is brought to you by, well, you, actually. We've been reflecting on the podcast, its history, and the incredible feedback that we've received from listeners across the world, and we're absolutely floored by how many of you really care. I mean, it takes a lot of energy and brain power and effort to put this podcast out while we're simultaneously growing positive energy, but we could not be more thrilled about each one of you out there listening and participating in this incredibly important discourse that's so badly needed in our industry. So here's the only thing that we're asking of you. Please take a moment, go to iTunes, and give the podcast a review, and then send the podcast to someone you think might care. Our audience only expands as the reviews come in and more people are out there sharing. You all mean the world to us, and we can't say thank you enough. Enjoy the rest of the episode.
Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello everybody. Hello and welcome back to the Building Science Podcast. Today's episode is one that I've been looking forward to for quite a long time. One great way to understand what we've been talking about on this podcast, building science, is to put it into a larger context. And I'm going to go ahead and start like this. One way to put it into context is for you listeners, take a moment and find some object in the room around you. Like it could be your keys, your sunglasses, your cell phone, maybe the room itself, any physical object. And think about, how did it come to exist? How did it come to be there? What sort of resource and information flows were involved in that? And even information flow, I've been enjoying Stanley Cup game recaps recently since I don't have any cable TV, and even the information flow, right? Somebody had to collect that video and put it online, so there's energy involved. So ultimately, all these things rely on a vast and complex interconnected web of resource and energy flows, and building science is no exception, right? What we're doing is we're studying the application of physics and engineering to architecture, right? And architecture being the conception, production, and operation of buildings and homes. So building science classically is, we look at the enclosure, the mechanical systems, the climate as a system, and more progressive thinkers like positive energy are putting the occupants' health and comfort as a system in there. And also, of course, the systems of professionals, right? Architects, owners, developers, builders, appraisers, underwriters, the subcontractors. All of those people are an interconnected system of systems. So it's all connected. Nothing stands alone. It's all, again, a vast and interconnected and complex web of resource and energy flows. And as such, building science is an application of systems theory, or a systems theory approach to buildings and homes. And here's where we start to get into today's subject, right? So systems theory or systems science is an interdisciplinary study of systems, right? They have interrelated, interdependent parts. Changing one part of the system affects other parts. And what we want are positive outcomes. We want to learn how we can change and adjust the systems to get more of what we want and less of what we don't want. And so when it comes to building science, we talked about what the main systems are. They're the people, the buildings, the environment. And so basically we're studying the interactions of living beings and their environment, which is ecology. You can Google ecology or wiki it, and you'll see, here it is. Ecology is the scientific analysis and study of the interactions of organisms, so we could say living beings, human beings, and their environment. So when we take systems theory and apply it to ecology, at least I'm going to say we get something called systems ecology. And that is where I'm going to introduce our guest today. We have the honor to talk to Dr. William Braham. He's a professor of architecture at the University of Pennsylvania, and he runs the Curriculum and Research Center in Environmental Building Design. We had the honor to meet him through one of his students, Elena Zambrano, who works with Overland Partners, and we have the honor to work with them. And I think you came to one of our happy hours, and we gave beer to you and your students. Is that right, Bill?
It's always a great way to meet.
And did I say it right? You're a professor of architecture at what university?
Yes, University of Pennsylvania.
Okay, good. All right, so would you like to introduce yourself any more fully than that, Bill, or is that fine?
You have asked me, where this work falls, and maybe that's not a bad way to give a short introduction.
Please.
Not the bio, but about 15 years ago, I co-edited a book with a colleague called Rethinking Technology, which was a book for architects looking at theories of technology and architecture, or architecture and technology, or even things a little bit outside that. And our broad argument was that something new had come up in architectural thinking, well, thinking in general in the 20th century, which was understanding things as systems. And so we collected lots and lots of examples of that and put that together in a book, which has actually been pretty successful. And it got me thinking, one, more broadly, and two, reconnecting up with the little bit of engineering background I have, and was the beginning of the program I teach, the research unit I run, and so forth, which when I first finished that project and thought to try and organize this more concretely for architecture students, I went back to find Howard Odom's book that I remembered from the 1970s, which conveniently was reprinted in 2007, called Environment, Power, and Society, specifically because I remembered the diagrams that he had developed. He had developed a whole system of diagramming, and that really began the project that we're talking about today. The book I published, which comes out of the program that I teach, and in particular a course I teach called Ecology, Technology, and Design. And Odom both sits at the heart of it and has also allowed us to do what I think architects do very well, which is to see lots of connections between things, to understand that buildings sit at the middle of lots of different scales of interaction. And if I can, be the professor for 10 seconds, Kristof, you said everything is connected, and that's true. But I think the more important thing that we realize once we get documenting these things is, although everything is connected, some things are more connected than others, and it's understanding what those are, which things matter the most to the topic you're interested in. So obviously, I'm mostly interested in buildings, so I go looking for exactly that. What are the causes? Why are buildings the way they are? Why do they do what they do? How could they be done, or how could they do things differently?
Mm-hmm. And with that, everything's connected, and yet some things are more connected than others. Can you give an example there with a building?
Yeah. Well, with buildings, on the one hand, I say this a lot, that you can build an incredible, say, positive energy building. You've done everything that correctly, but if you build it in the wrong place or for the wrong purpose, it can all be a waste. Meaning, literally, if there's nobody to use it, or if it requires so much use of resources in order to get to it, to use it, you've lost sight of what you were trying to do. And I'm not talking about any specific project, but just the fact that when we as architects start our work, we are correctly concerned with the building kind of as an object. You draw a boundary right around it and say, we just want to track how much energy and how many materials and how well will it serve the client, all of those kinds of things. But you do have to keep your eye on a whole larger set of causes, and I would also say effects. So something like global climate change is the result of the cumulative result of lots and lots of tiny individual decisions. And it's easy to miss the point when you're looking at just a building and thinking about the relative cost of making some improvement or another. So global climate change is actually a perfect example of seeing the relation of parts in a system to the total ecology.
I get it. Yeah. So if you did a net positive energy building, however, it was a 2-hour one-way commute to the nearest grocery store, and there was no public transportation or something like that. Yeah.
Exactly.
Mm-hmm. And so that's a good example of how the systems ecology perspective can inform your view of the world, right? It's cycles and systems and networks. And that was Howard Odom's majesty. Actually, let me interject here, make sure listeners have heard. So we're talking about Howard Odom. The book is Environment, Power, and Society for the 21st Century. That was the revised version. It's tremendous. It's not made to be a page-turner, but it's definitely worth taking a look at. And coming out of that, applying that to architecture, Dr. Braham has written Architecture and Systems Ecology. And that book, for me, it just was a jaw-dropper. I mean, it has absolutely changed my my relationship with the world. Like, I drive around, when I'm flying, across transatlantic, my mother happens to live in Europe. It's just, I think about everything as these resource flows and energy flows. So one of the challenges when we're thinking about that way, we try to think about the interconnections, right, Bill, is that it's not always the same units. It's hard to find a common unit to do the math in. Is that an accurate way to talk about?
Yeah, and I think before we jump all the way there, let me say, what the way I often explain systems ecology, and I should say, my discovery of Howard Odom was very much what you just described. I mean, I love hearing you talk about the book that way, and every author loves to find real readers. But Odom had very much that effect on me. Just, oh my God, I can't believe I didn't recognize that, that possibility, that formation, and so on. But I think just to put all of this in perspective, Howard Odom often credited, I won't go into the whole long history, but he credited a number of people who came before him in the 1920s and 30s who recognized first that natural selection, the stuff that everybody was worrying about and is the reason ecology even exists as a science, right? Because species evolve in response to pressures of one kind or another from their environment, but very quickly people realized the environment itself changes and species actually work to change their environment. And humans are not the first species to change the environment. We've just been the most recent and the most successful at it. But the key breakthrough for Odom, or the thing that got him started on his career, was another scientist who recognized that if he tracked initially food exchanges, who eats who, where does the waste go, etc., and ultimately tracking energy exchanges, that you could reveal the structure, organization, and ultimately even the sort of development or evolution of different systems. Those guys were looking at forests and wetlands and kind of classic ecological situations, but basically they found that if they kept good track of who ate what, where did their waste go, somebody spent some time making something, some creature spent time making something that provided a habitat for something else, all those kinds of interrelationships, they got a picture of the working of the ecosystem that they hadn't gotten by any other form of observation. And Odom started from there and just took off. He recognized that it applied just as well to human constructions as it did to we'll say, not inanimate, but unconscious systems, although maybe they're not wholly unconscious. But he literally proceeded from that long chain and ultimately realized that energies came in different qualities. And we know this, that if you're trying to run your computer, having a container of hot water is no particular use. It's just not a high enough quality form of energy to run your computer. And vice versa, you could say using electricity to make hot water is kind of throwing away some incredibly high quality, very portable, very flexible forms of energy. So he, by tracking this stuff in systems, developed a way to describe the difference in qualities among kinds of energy. And broadly speaking, in fact, this I think was his first big principle or statement of principle on his own. Broadly speaking, systems are doing whatever they can in order to maximize their power, to concentrate and increase the useful forms of energy and resources that they have available to them. And they do this at all different scales. And, you could look at human society as a whole and recognize that tendency. And I was really struck the other day. I've been reading Kim Stanley Robinson's, it's a revised novel of his called The Green Earth. And in it, he just notices at one point, it's very much it's actually a great novel, recommended highly, and it's making real the sort of human dimensions of some climate change effects. But he has a couple of scientists sitting around and realizing that individuals within the system can notice what's happening, but the system itself is not aware of what it's doing. Nobody planned for it to do it, and yet by the collective actions, like the invisible hand of the market, the system is pushing to maximize its power. So that was his first really big principle, and with variations, most ecologists will agree with the statement that ecosystems of all kinds, including ones with humans in them, are maximizing something like power. So
What does that mean exactly? Maximizing power. So I know power is the rate of energy transfer.
Right, and so it's really important to distinguish between energy and power. Energy is the amount of capacity you have to do work. But if you take my favorite example, which I've stolen from others, of you have a pile of wood, and you're facing a cold night, and you have two choices. One is to build a shelter with the wood, and the other is to burn the wood and make a fire. Well, stretching that analogy out, if you build the shelter can only hold so many people. So that shelter can keep, we'll say, 10 people warm for as long as that shelter lasts. We'll say, 25 years. But if you burn the wood, you can keep 10 people warm for, let's say, a week, or you could keep 1,000 people warm for one night. Maybe not 1,000, 500 for a night. So the rate at which you're able to burn the wood is much greater, right? It has much more power, or it can deliver that energy at a much faster rate. And it's also, you can choose what rate to do it at. So in that sense, the burning of the wood is a much more powerful enterprise, whereas the making of the shelter, which has a lot to say for it, and there's a lot of benefits to it, but it is something which is operating at a lower power level. It's delivering its value at a lower level over a much longer time. And another example that I think helps a lot is we all, every day, all the time, trade energy for power. So if you're driving your car to the market, or riding your bike even, but pick your form of transportation, if you go more slowly, and this within some restrictions, of course, and so forth, but sticking to the gear ratios and all those things. But if you go more slowly, you will get more mileage out of your gallon of gas. On the other hand, we all are weighing that against what are the other things I'm going to do with my time? How long do I want to take to get to the supermarket and so forth? And we all trade. We're like, man, I'm going to go a little bit. I'm going to go fast enough so it seems, I make some calculation without thinking about it as a calculation about how fast I need to get to the supermarket and back. And we pretty much all, in almost all these contexts, push for more power and sacrifice energy, or energy efficiency, I guess I would say, up to some level, depends on the system and so forth. So having power, and in fact, Odom would say, this is what goes back to those first observations, that this stuff is evolutionary in a very straightforward sense, which is that the systems that can command the most power win. And then they're not necessarily fighting with other systems, but they're simply growing faster, obtaining, getting to resources first, obtaining more resources. And this is, arguably true whether we're talking about, algae in a pond, or whether we're talking about, competing human civilizations. And he was first writing this stuff in the 1970s during the energy crisis. And as much as he is an environmentalist, one of the things that a counterintuitive remark of his that surprised and I think frustrated his students was, it's crazy to simply pursue energy efficiency thinking that you're going to save the world or change the planet. If there's another competing group, and in his mind, the Russians were the group that he was worried about. If there's another civilization that is willing to consume those resources at that rate, you have to recognize. So it doesn't mean you shouldn't be efficient, but it means you have to recognize that larger dynamic of one group versus another trying to balance their relative power, or their race to use the resources that are available to them.
For some reason, that reminds me this like if the U.S. were to be consciously deciding, no, we're going to be moderate with our energy use, and the Russians, take the lead in the world economy. Kind of reminds me of the Raiders of the Lost Ark, where the guy meets Indiana Jones and he whips out his sword and he does this fancy thing, and Indiana Jones just shoots him.
Right. Yes.
Asymmetrical.
Well, and it's all. Yes. Mm-hmm. Exactly.
Well, just briefly, I want to touch in on a really cool metaphor that I read. I prepared for a presentation a while ago on the difference between energy and power. If you had roughly 24 gallons of gas in a tank, obviously that represents a certain amount of energy. You can drive, a hypermiler drove from Houston, Texas to Richmond, Virginia on one tank of gas in a Camry, 24 gallons. The same 24 gallons can take a dragster a quarter mile. So you can see there's much more power. But back to your core message, I mean, it's so deep, and I really hope you guys listening can hear it, that we want to maximize power, and yet isn't it true, Bill, that that can lead to ecosystem collapse in some ways? That can lead to this powerful entity using up its fuel, and then
Well, and I think this goes to the puzzle. We have as we'll say smart people thinking about the implications, because, and this is why I cited that Kim Stanley Robinson observation, which is the system is blind. So the system is, we're just tiny parts and cumulative parts of all this of these systems that we're working in. So, yes, we're doing this in order to understand where the things we work on sit, how they affect other parts of the system. But I think it also means we have to be strategic about what we do. We have to be clear-eyed about the effect of our individual actions, the kinds of levers that are available to us. So I don't think it means that you can't, that the systems don't change, but I think we do have to be clear that at some level these things are always, we'll say, somewhat political, somewhat social, certainly natural. I mean, that those things are always co-present, and we often, at least in my world, we often separate building science from other ways of judging buildings. And I think part of the message of systems ecology is that those are all different aspects of the same endless set of experiments to figure out, both what's the best way to build and what does the system want is a way to think about it. The system will, whether we've designed the best possible building in the world, the system, meaning the collection of people and real estate rules and all of those kinds of things, will select the buildings that help it maximize its power. Whether the individuals making them or choosing them know about it in those terms at all.
So an energy efficient, net positive energy building is actually only is achieving its optimal benefit when it's done in a way that helps the system it's in maximize its power.
Exactly. But I would jump up a scale, which is always a great tactic for somebody talking about things, because I would go further and say, so net positive, building, we don't have to describe it. It's this almost perfect building. Right now, it has an additional value as an exemplar or as a demonstration of something that's possible to help move larger populations of buildings. So when I talk like this, it sounds as if all that matters is what's the norm, or what, the vast majority of buildings are built exactly to the minimum energy and other codes that are required. But if you think about how to shift that needle, then the value of that building is not just the energy it saves, but also its ability to show other people that it's possible to be a tool in changing codes and so forth.
So fascinating. You've just moved to the realm of information and human psychology as you've connected that to sustainability, right?
Yep.
And so back to your example, I mean, the difference between material resources and high-quality fuels, I'm remembering, it might be from your book, but I'm remembering that there's enough BTUs in all the world's oceans to power our global economy for many hundreds of years, but it's at a very low exergy, a very low energy quality. So like you said, you can't run an economy off of that energy, but you can run an economy off of relatively high voltage electricity that's moved through transmission lines. And now, so you have that building, so you had that pile of wood, and you had a choice between burning it or making a structure out of it. And in our society, we have glass skyscrapers, right? So it's obvious the choice there. It was burn the energy mainly. The enclosure is mainly a suggestion. And so can systems ecology help us define how good the enclosure should be relative to the energy it needs to produce shelter?
Yeah, and before we jump to that again, I'm using all these rhetorical tricks that lecturers do. But
please, yes, I like that.
But before we jump to that, which I think particularly for your audience would be a really
that's
kind of interesting point. To put it in context, Odom's second principle, well, second and third, but his second principle was, in the pursuit of maximum power, systems develop hierarchies. And we all recognize this. I mean, we see this everywhere. We certainly see it in every human society that's ever existed, that there are essentially specializations, which, if they work together, increase the productivity, the size of the society that they're supporting, and so forth. So if we start looking around, we recognize those hierarchies everywhere. The classic one that we all learned in biology class is the forest food chain, from green plants to herbivores to carnivores, and they are mutually interdependent and mutually regulating. So, the lion is not the king of the jungle. The lion is actually the feedback. It's like the thermostat for the jungle that keeps the population of herbivores from growing to a size that kills off all the green plants. My local forest here, owned by Swarthmore College, had until recently nothing green below about 6 feet because the deer population here is radically out of control and the forest was dying. So couldn't introduce either wolves, or we used to have some wildcats here, couldn't introduce either of those back into the population. So they cull. The humans go out and hunt the deer back to a population that allows some trees to repropagate and so forth. So we look for we see the same kinds of things happening in human systems, both hierarchies developing and also hierarchies getting out of balance. And in our case, it might look like there are too many predators around, but that's perhaps for a different conversation. So that was his second principle, was that systems develop these hierarchies. They are both hierarchies for self-regulation, and they're both hierarchies which produce at the high end very, very valuable, very highly concentrated either energy resources, food resources, concentrated materials, those kinds of things. So electricity is an example of a very, very highly concentrated resource. So it's both very expensive, and if you're just looking at it and thinking how to make life more efficient, you would get rid of electricity. But on the other hand, it's valuable as a tool and a regulator, and maybe information goes one step beyond this for the total system. So first principle, maximum power. Second principle, hierarchies of energy exchange develop to regulate and support the whole system. And then his third late in life principle, which relates very much to buildings, was to recognize that similar to, but actually separate from this concentration of power, were concentrations of materials, or purification and concentrations of materials, which happen in parallel, So if you think about, any of the metals, which are just easy to see, look around the room you're in now, there's a bunch of metals, which we know took a bunch of refining from whatever ore they came from. So I happen to be looking at some aluminum, another piece of copper over there. So, you look at those and, right, it's pretty intuitive, right? It takes a bunch of physical work, it takes a bunch of heat, it takes a bunch of chemistry, it takes a bunch of transportation to get that piece of purified metal to be there. So we keep track of that, and life cycle assessment keeps track of that. But what about the ore? Because the ore is actually a fairly concentrated version. That metal has been concentrated in the ore by a bunch of typically biological and geological processes. So we don't go around. We could, if we had an unlimited supply of energy, we could simply filter the air or the dirt or the seawater and ultimately concentrate out of it almost any material we want that's present in background materials in the seawater. But it would take an incredible amount of energy. You would need an unlimited source of energy in order to do that work. So what we do is
say you can make steel out of seawater.
Exactly. But right, where are you going to get all that energy? So what we do is we look for places in which the global geobiosphere has done the work of getting it to a sufficient concentration that it's economical for us now to make those changes. And many people have pointed out that we're getting to the point with some of the metals, some of the things that we've been extracting as ores, that human landfills are beginning to have concentrations of those materials that rival those in ores. So it may actually be economically worthwhile to start mining landfills instead of going out and mining, lower level ore concentrations out in wherever they're located.
Fascinating. And
So
of course, you're touching in on fuels. Coal, is becoming economically disadvantageous to go after, and natural gas is still okay.
for the moment, yeah.
Yeah.
Well, and those, and I mean, it's a big subject on its own, and in a way more challenging, because there have for over 150 years there have been people who have been trying to directly equate energy with currency, and to say, that our currency should be based on some energy unit, and at least from my reading, and I'm certainly not an economist, currency is simply it's more powerful in a way. It's more concentrated. It's more fluid, and so it actually does allow more all the time us to transfer resources from one place to another, or the power to exchange those resources. Now, no question, currency can get out of sync. I mean, there are inflations of many different kinds. It can get out of sync with we'll call it the biophysical basis from which it's born, and so some parts of economic cycles can be understood in that way. But we were trying to loop back, weren't we? I was doing this long explanation of Odom's 3 points to try and get back to your question about building envelopes.
Correct.
Which I think, again, I always approach this as an architect, and to some degree, the envelope is one of the last things that we as architects really have something to say about. But even there, we have to turn to other experts all the time.
Right.
But we did a study. The example that runs through the book is my house. I think it's inevitable that people who do this kind of work end up using their own house as case studies. And we have started applying this to other buildings. So this isn't just a personal story, of course. But one of the questions we would like to answer is, or one of the things we're always trying to answer is what things are worth doing, or what things are more efficient, and does looking at things in this broader context. We haven't even introduced the concept of emergy, which, having done all this talking, is probably simpler now, which is to say,
I was wondering I was like, how are you going to talk about your house analysis?
So with all these examples, whatever it is, coal or copper or whatever it is, if you just go through, and there's some serious accounting here, and add up all the work you had to do and all the work that was expended to make the resources that you're using to make any given thing, doorknob, telephone, vinyl siding, whatever it is, you can there's pretty simple math to put all of those in the energy units, And the term, a little bit unhappily, that Odom coined for that is emergy, meaning quite sensibly embodied energy. But because the M and the N are so close, it can be a little bit confusing. But anyway, there's good, pretty straightforward algebra for adding all of that up, and it has two effects. One, you can by looking at the amount of emergy, of the amount of stuff, work, and resources expended to bring some product or service to the building, you can identify both their value, and I mean that in two senses. One is the cost you had to pay for it, which is how we typically think of it, but also presumably or possibly its value to the building. And that's ultimately what we would like to know. It's not that we want to stop making buildings that are smart and sophisticated and able to, do lots of amazing things for us, but that we want to understand both how to do that in the best way possible and how that can fit into a larger larger ecosystems. So what we do to think about this is literally add up everything that goes into every component. The simple example, which I elaborated in the book, was to ask which of all the things in the building, which things affect the thermal comfort, the temperature of the building. And we're going to ignore humidity a little bit for a second, which I know you can't really do in Texas. But if you just look at what does it take to heat a building and what does it take to keep a building cool, my climate is here in Swarthmore, so it's a temperate. We have real winter or something like winter and something a lot like summer and some swing seasons in between. So we go through them with every component, whether it's the building envelope, sun coming in the windows, heat from a natural gas furnace, cooling, heat removed using a typical air conditioning unit, the whole spectrum of things, right down to how much heat is provided to the building by the people who live in it, digesting the food that they're fed and giving off heat. And so in each one of those cases, you can go and add up all the things it took to bring that to this place, to this building, to have these effects. And you can also then quantify how much of an effect they have in keeping the building warm or cool. Obviously I can't do the math in a podcast, but it's certainly in the book, and really is just algebra. The happy result for this building, and by the way, this is not a universal statement about all buildings. This is an analysis of this particular mid-century modern building built in Swarthmore, Pennsylvania, according to some very cool, but also, very peculiar approach to the climate. And it turns out almost an order of magnitude or two greater than anything else, that the building envelope is the single most effective way to keep the building warm or to keep the people in the building warm. Meaning you are spending fewer of your total resources per unit of heat that you provide to the building by building the envelope. I'm flipping to look for the chart right now. That's considerably better than the sun coming in the window, because there's not quite as, because the effect of envelopes is so big, but also because the windows themselves are a pretty refined and slightly expensive product, and considerably better than the heat that comes out of the furnace. The most expensive way to heat your building, or the most resource intensive, we don't always pay economically for these things, but the most resource intensive is the heat given off by people, because ultimately that is, think about, if you call it a waste product, that's one way to think about it, but we're essentially burning this incredibly high quality fuel, the food that comes through our retail food system. So that's very expensive. So now the reason I qualify this by saying this is for this particular building, this building was sort of designed, or was designed with principles you would recognize as passive solar heating principles, sort of present. It wasn't explicit, but if you put on those glasses, the building is actually reasonably well configured in those terms, and we insulated the heck out of it when we bought it, and those kinds of things. So what I'm getting at is that makes the value of the envelope much, much greater for heating. If we look at it for cooling, it is not at all well designed for cooling. In fact, it's really designed to be a box to trap heat. And so the value of the envelope for keeping the building cool is about the same as the cost for using the air conditioner to cool it. So that is not an argument that that air conditioning is good and heating with a furnace is bad. It's just that this is an envelope which we now recognize was not designed according to any principles that would help it achieve cooling better. And there's a couple of simple things you would do in this kind of climate that would kind of dramatically improve that. But we were looking at an existing case study.
Fascinating. So I living where I live in Austin, Texas, I have to go back into that about air conditioning and the enclosure, because the enclosure here can actually keep the heat out, right? If I have high albedo roofing, if I have good shading on my windows, I mean, windows are going to exist because humans are in there, and making yourself feel a sense of beauty and whatever it is, that psychology aspect is important as well. So what about air conditioning versus enclosures? What about cooling them?
Well, that's why I say, so this building was not, none of the things you mentioned or probably, could mention that you would do more as a matter of course in Texas to keep the heat out and allow buildings to do it. None of those are done in this house. It's almost impossible to get this house to ventilate, and so on. So those things would make a huge difference. And I think, one of the things that is always helpful for students to recognize, and it takes architects a while to learn to think this way, but that in one sense, heating is kind of easy because, there's lots of sources of heat or waste heat around, sunlight and internal gains of different sorts. And so you're designing just to hold on to that heat, and you can keep a building warm that way. With cooling, every source of heat is your enemy, or every source of heat is something you're trying to get rid of. So it's both a question of keeping the heat in the environment out, but it's also a question of getting rid of the heat that's developed inside the building. So those are both things that can be done obviously better than this house does, and are practices that you would be pursuing in Texas. But it does get us to an interesting question, which a lot of my colleagues would step back from, which is there is probably a place for that high emergy intensity, that high value, expensive cooling process that comes with dehumidification in particular, and air conditioning more broadly. There probably is a role for some of that. How much? I actually, one of the things I would like to work on, or have sort of on the list to work on, is to do this analysis for building in a hotter, more humid climate, and to think it through more critically from that dimension. Because the ethic that I often encounter among ambitious colleagues is we've got to design purely for buildings to surf the climate. And I think that is absolutely the first place you start with any building design. Both right. Know the climate and know how a building can change its features either through the day or from season to season in order to, ride those changes. But at what point so one of the questions we then want to ask is, at what point is it crazy or more expensive to be investing in the envelope than investing in some other system? And it doesn't always have to be classic mechanical air conditioning.
It could be solar
PV. Yeah, exactly. Or, I have colleagues who are really excited, whose work has been focused on Singapore, but who are really interested in desiccant-driven systems, so right. Solar-driven desiccant systems for removing humidity, because they're already, Singapore, there's already a cultural acceptance of a warmer temperature. Everybody just dresses for it, everybody lives it, but we all know that pulling the humidity down makes that huge difference. So if you walk in out of the street and you walk into someplace which is drier, and even if it's not radically cooler, it completely changes your experience.
That's right. And it doesn't just make it better from a thermal comfort perspective, but as we know, the indoor microbiome changes, and that means different critters and different biology shifts when it's drier, and that tends to promote healthier indoor conditions. So it's all connected. We've just got our radiant system running here at the office, And that's a huge deal in the sense that to cool our building, we need a 60-degree supply of water, and to heat it, we need like a 90-degree supply of water. So suddenly, instead of asking my heat pump, we have a very efficient VRF heat pump as a alternate system, but it makes 36-degree refrigerant in the summer, and it makes 140-degree refrigerant in the winter. So instead of 36 and 140, now I have 60 and 90. But I still need to solve the dehue. But I need to solve with much less air mass. I just need it for drying and filtering and ventilating. I'm only moving air for that instead of air as a primary heating and cooling source. So as you say, there's different emergy inputs into that. And I'm thinking we're getting close to the end here probably. Obviously there's so many different directions this goes, and I really encourage you listeners to read his book, Architecture and Systems Ecology. It should be required for anyone that has anything like efficiency or sustainability as part of their mindset or part of their mission statement. But you mentioned drawing the boundary, and we talked about, there's like the classic example from, maybe we can even put it in our show notes. It's from Odom's book where he has a house and he draws a kind of rectangle around the house, and what's coming into the rectangle, so we're outside of the enclosure now, is materials, it's fuels, so he's just using oil, it's groceries to keep the people alive. He didn't put information, which you touch on in your book, but so we'll skip information because he didn't. So he talks about materials, fuels, and groceries, and then you go into the house and you have the people that eat the groceries, and they come back out fed and well rested, and they now have a job that gets them money that they trade for more fuel and more groceries, and of course more wood for repairs. So you can see that cycle. I guess there's not really a question here, but it talks, he does it in illustrating it in his energy systems language, which is amazing.
And I think that might have been the diagram that made me realize, oh my God, this really could be extended into architecture in a way that answers a bunch of questions that aren't answered by other things. So one thing I can do is make a plug for the part of the subtitle of the book is Site, Shelter, Setting. And one of the things that doing this, using his energy systems language, and a lot of the conventions there are pretty intuitive, stocks and flows and all those kinds of things for people who thought about systems at almost any level. But one of the things that came clear after really trying to apply this was there are, broadly speaking, 3 scales of activity at which we can usefully and meaningfully analyze buildings. And I think this is kind of what I had in mind when I made the point that yes, everything's connected, but it's actually kind of lumpy, meaning that there are lumps of stuff that are meaningfully connected, and they can be detached from their other connections in order to study them without doing a disservice, meaning you're finding kind of natural boundaries in there. Obviously, shelter, the stuff we've mostly been talking about, building an envelope and doing different kinds of equipment to make conditions that would make people comfortable, both thermal and humidity and light levels, all those kinds of things. That's kind of primary job. It's what architects, I think, are best at. It's what we think of buildings as doing first and foremost. And so that's it's well-researched, well-defined. It's what we mostly mean by building science, is the things that go into that. Within that, I think there's a separate category of things that I'm calling setting, because everything had to start, of course, with an S, but really have to do with what do people do inside them, whether it's a business or a home and those kinds of things. And this has always been puzzling, or I think it makes energy analysis of buildings a little bit confusing, because the rules for efficiency and relationship to the client that apply to the shelter don't apply to this stuff. It does have its own logic. So you're ultimately asking, what do people do? What do they do with their time? What's the value? What's the economic value? What's the social value of them? I mean, it connects up to lots of other topics. So we can't just go in. In fact, I've had one of the examples. I had a colleague who former student, called me very excited. He's doing this deep emergy analysis of the building. He's located in the University of Florida. And he said, I figured it out. We can just really improve the emergy footprint of this building if we just close it at 6 p.m. every day. If we make all the people go home instead of staying and working in the building. I was like, well, that's great, but what are they gonna do? He goes, well, I don't know. They'll all go home. They'll all go home and work there. I'm like, well, so there's still. It's one of those things that you can't you can't draw the boundary just around the people while they're in your building. You have to then see that other pattern. So that's a problem that slips out of the envelope of the building, and that's related to the other one, which I think is also very familiar to people who think about buildings, which is, again, what I'm calling site, and that has to do with both where you choose to locate a building and its capacities. And projects we're involved in, decisions we've all made personally, all relate to this. You make some calculation about, if I live there, I'll have to commute this much, so there's costs involved with that, and I'll also have to pay these kinds of taxes, just to take the two really most obvious ones. And at least in my city, if you move farther out, your taxes drop. At least, there's certain boundaries. But if you move farther, your taxes drop, but your commute goes up. And so you're trying to balance those kinds of things. And if you're a business, well, I actually need to be near where there's lots of people, and then the land is more expensive and the taxes are more expensive. So those are not a building design question. Those are you could call them a real estate question, but I think it's a city and self-organization question, which very much affects broader issues of sustainability. So I think those are three kind of separate scales, maybe inspired by Odom's, people, furnace, and he even, I think, accounts for the rats that live down in the
Right.
presumably in the basement of that.
And the termites that are eating the
Exactly.
wood.
It's a great diagram.
Yeah, so the extra food. So that's beautiful. So site, shelter, and setting, those three scales. And it was actually that, Bill, that really just lit my mind up like a Christmas tree, in the sense that I had been studying enclosures and mechanical systems and people. So my box was just around that, the house, let's say, or the building. And to realize, oh my goodness, this building is part of a network, part of a system. And in fact, even the interior of the building is there's a system happening there. I think that's what's really profound, and that's why I consider it the science of sustainability. And I'm sad to say, I'd like to get your final thoughts, if you could, if it's possible, even to synthesize all this about buildings and make some comment about, maybe even something kind of crunchy comments about sustainability. Like, I'll define it, right? The classic definition is that you and I and our generation lives in a way that doesn't impair future generations from having the same access to this lifestyle that we have.
Well,
can your book comment on that?
Yeah. Well, I'll say some things maybe that aren't in the book, and also maybe I tend to put things in three, so maybe I'll do that. But Odom, a couple times, made the remark that sustainability, as he encountered it, which really, of course, means sustainable development. It came out of that whole argument about population growth in the 1970s environmentalism, but that sustainability writ large was really an effort to reproduce the Climax Forest. And I think it's both a really great model, and there's also a caution that goes with it. And first of all, it's a fantastic model, because Climax Forests, if you don't know the term, are, temperate ones are the ones we think about mostly, but applies as equally to rainforests. But these are hugely complex ecosystems that build up over many generations. But in their mature form, achieve an almost perfect recycling of materials and use almost every bit of the energy that flows through them. They're primarily driven by sunlight and rainwater, and some nutrients that are brought in that come in. So these are open systems. They only exist, of course, because there's this flow of energy. But what they do is they produce zero waste, or virtually zero waste. And so I think that, in a way, that's the for me, the better approach to sustainability, which is to eliminate all these, to find ways to close all the loops and eliminate all these forms of waste and pollutants, and to live within the budget. We would not, there are probably other limits beyond them, but we would not be struggling so hard with the fossil fuels if we were once we face up to and capture the CO2 or the carbon, the greenhouse gas pollutants that they're emitting, or we would be approaching them very, very differently. We probably have heat effects.
Kind of one powerful open loop that could be closed with
and
the CO2 cycle.
Yeah, and it's perfectly closable, and it would mean giving away some of the energy that we're pulling out of it, but arguably at a whole it would make us more efficient. So I can close with the trilogy I often try to pass on to students. And I think the caution is that efficiency is not enough. I mean, efficiency is like our first tool as environmental designers, environmentally minded architects, and so forth. But it is, it's never enough. So I always say, first you start with efficiencies, then you look to renewable energies, and then you're ready to start thinking about paradigm changes. And depending on the scale, depending on what you're talking about, that can be lots of different things. But, you're only going to get to that sustainability by thinking through all three steps.
Beautiful. Efficiency, renewables, paradigm changes, exactly. And that's what these ideas can do for us. And that's what, people like you and I, one of the products that we hope to deliver, I believe, is education and advocacy in pursuit of paradigm shifts, right?
Perfect.
It would be nice if solar panels and a net zero energy building was it, but it's not that case. Well, thank you, Bill.
Thank you.
Truly a pleasure. I enjoyed our conversation, and thank you all for listening, and we'll see you next time.
Don't forget, please leave us a review on iTunes and share this podcast with your friends.